Okay, we're going to look at some applications. Suppose after an initial dose of 60 milligrams, a flea medication breaks down at a rate of 20% per hour in an animal's bloodstream. This means that each hour passes, 20% of the medicine is going to be used. So the question is, we want to write an equation to model the medicine amount in the bloodstream over time. Okay? So, if 20% is getting used up every hour, how much medicine is staying in the bloodstream every hour? If I get rid of 20%, I get to keep 80%. So, we are looking at y equals what we're going to start with. So that would be 60. And if we're going to get rid of 20% every time, so 1 minus 20%, however much time there is, so we're going to keep 80%. So I'm going to go ahead and just change 1 minus the 20%. I'm just going to change this to 80 to make it look a little bit easier to do. Now we can fill in our chart here based on that. So if we start out with 60, and in our calculators we want to take and get rid of 20% or keep 80%. So 60 times 0.8, we would have 48. And if I put 2 in here, 60 times 0.8 raised to the second power. So what's happening here is that we're multiplying by 0.8 every time in our chart. All right, let's look at another one. Okay, the half-life of aspirin's presence in the human body is 3.2 hours. If a person takes 650 milligrams of aspirin, about how many milligrams will be present in the person's body 16 hours after taking it? So this word half-life means that if you took 100 milligrams, 3.2 hours later you'd have 50 left in your body. You'd have half left. So every 3.2 hours, you're only going to have half of what you started with. Okay, so we're going to start out with 650 at the initial amount. And so after 3.2 hours, we're going to only have half of that. That's what half-life means. So we're going to do 650 divided by 2. So we have 325. All right, and we want to get up to 16 hours. Now we could do this again. Another 3. Oh gosh, so we're multiplying by 1/2 every single time. So we're going to start with 650 times 1/2. And then we're going to figure out how we want to see 16 hours later, but every 3.2 hours it will be cut in half. So we're going to do 16 divided by 3.2. I need to know how many of these I need. So it's 5. So y equals 650, 1/2 to the 5th power. Okay, so we're going to write the equation biology project. Nicole is investigating how fast a particular beetle population will grow under controlled conditions. She started with 5 beetles, and the next one she counted 15. So here's our table. So the second month, what are we multiplying by? We're multiplying by 3, so it is growing. So our rate is going to be bigger than 1. So if we write our equation, y would equal our initial amount times our rate, which is 3. It's growing 3 times. That's how fast it's growing. T for time. How many beetles would she have during the, let's say, after 10? So we'll put 10 in here. So y equals 5 to the 10th. Use your calculator. So then she would have 295,245 beetles. Part C. How long, I don't know how long, consider how long it would take to reach 200 beetles. So 200 we're going for y, and then we're going to solve for t. So we divide by 5. So we get 40. So we need to figure out and write these as the same base if we can. I don't think that's going to happen. So what we're going to have to do is to figure out, by putting this into our calculator and seeing where the two will cross each other. Or we can continue our chart. So let's go to our calculators. We're going to put these in. Okay, so I put each side of the equation into the y equals. I'm going to hit graph. And I need to change my window, most likely. I'm going to do a zoom 6. Okay, I can't see the 40, so I'm going to go to my window because right here y equals 40, so on my window my y-axis needs to go up to a little more than 40 to be able to be seen. So we'll put maybe 50 and hit graph. Okay, so here's our intersection point. So second trace, choose intersection, hit enter a few times. So it's right around a little bit past 3 months. Almost, well, 4 months.